So Jai Hind everyone. Today I am going to discuss nuclear fuel cycle and nuclear safety. So it is related with subject energy science and engineering. Subject code is KU043 or KU033. So today we will discuss how nuclear reactor uses uranium, and before it goes to nuclear plant, so how this is being calibrated in various form. Okay, so for this is called as the nuclear fuel cycle. So that means mining stage of uranium from uranium mines to the calibration as uranium rud for nuclear reactor. This complete process is called as the nuclear fuel cycle, and how nuclear safety is maintained in during this process. So that will be discussed in today's lecture. So first, nuclear fuel cycle. What is nuclear fuel cycle? It is the cycle, it is the series of industrial processes which involve production of electricity from uranium in nuclear power reactor. Okay, so first in this fuel is uranium. Okay, so how uranium is being mined from the mining process, and then it is calibrated as uranium fuel rud for nuclear reactor. Okay, so and in that nuclear reactor, this uranium rud is used as fuel for producing electricity and nuclear power plant. So the nuclear fuel cycle is basically a series of industrial processes which involve the production of electricity from the uranium in its reactor. Okay, so uranium is relatively very common element and it is found out across the globe. Okay, so it is very abundant in nature. So it is mined in a number of countries and must be and it is processed before it can be used as a fuel for nuclear reactor. Okay, so in this processing there are various stages. Okay, and all these complete stages, those are combined, that is called as the nuclear fuel cycle. So uranium is used in nuclear reactor for producing electricity because it is very much abundant in nature and it is available across the globe. Okay, so it is a very common material. Okay, so fuel removed from the reactor, and when it is used in the nuclear reactor, it is removed from the reactor. Okay, because its useful life has been ended. So fuel removed from the reactor after it has reached the end of its useful life and can be reprocessed again to produce the new fuel. Okay, so that is not completely wasted. We can reprocess that. Okay, we can reprocess the used uranium rod again for producing the new fuel. So the various activities associated with the production of electricity from nuclear reactions are referred to collectively as the nuclear fuel cycle. Okay, so the nuclear fuel cycle starts from the mining of uranium and ends with the disposal of the nuclear waste. Okay, so mining of uranium, okay, from its mines, and then disposal of its nuclear waste after producing electricity is the complete nuclear fuel cycle. So with the reprocessing of used fuel as an option of nuclear energy, the stage from a true cycle. Okay, so ultimately what we do, we used uranium can be again reprocessed for using it again. Okay, so these are also the part of fuel cycle. So see, this is the diagram of the nuclear fuel cycle. So here we can see here. So first, mining stage is there. Okay, so here mining stage is there. So then after mining, U3O8 goes for conversion to UF6. Okay, so in mining we receive U3O8 that goes for conversion to UF6. Okay, and this UF6 will contain 0.7% of U235 only. Okay, so only 0.7% of U235 is not enough for producing electricity. So this goes for the enrichment. Okay, for this is the enrichment part. So after enrichment, this 0.7% of U235 reaches to 3 to 5% of U235. Okay, so complete sample of fuel will have 3 to 5% of pure uranium 235. So then it is fabricated. Okay, so fuel fabrication will be there after enrichment process. Okay, so then depleted uranium will be go for MOX, and then after fabrication fuel rods are created and it has been sent to the reactor. Okay, so this is the reactor where fuel rods are being sent, then used in reactor. Again we will use the uranium rod, okay, as a fuel. So then used fuel will be stored here. Okay, after it in storage process, again some of the fuel will be disposed, those are completely waste. Okay, the part which cannot be processed, and the portion of the used uranium which can be reprocessed will be sent for the reprocessing. Okay, so after reprocessing there will be after reprocessing we can form plutonium. Okay, so again plutonium can be sent for the fabrication. Okay, plutonium will be used as the new fuel. So next, in reprocessing process also there are some nuclear wastes, so that will be sent for the vertification, and then after vertification complete wastage, nuclear wastage will be sent for the disposal. So this is representing the complete nuclear fuel cycle. So here both excavation and in situ techniques are used. How uranium ore are recovered from the mines? So there are two process. Okay, so one process is excavation and second process is in situ techniques. So excavation may be underground and open pit mining. Okay, so in general open pit mining is used where deposits are close to the surface, and underground mining is used for very deep deposits. So if at the earth layer, if uranium is found at the level of 120-meter deep level, so in that case underground mining will be used. Okay, so and open pit mining will be used where deposits are very much close to the earth surface. So open pit mines require large holes on the surface. Okay, so in open pit mining comparatively larger holes are created on the earth surface, so that size of the hole is usually larger than the ore deposit. Okay, since the walls of the pit must be sloped to prevent the collapse, so as a result the quantity of material that must be removed in order to access the ore that may be large. So quantity of material in open pit mining is always large. So in underground mining, so relatively small hole will be created at the earth surface. Okay, so and the quantity of material, okay, so that must quantity of material that will be removed from the earth surface as a fuel, as a uranium ore, that must be considerably less than the in case of the open mining. Okay, so in case of open mining we used to create large hole on the earth surface, while in underground mining relatively smaller hole is created on the earth surface, and the amount of uranium ore that will be removed by using the underground mining, okay, so that is comparatively less in case of open mining. Okay, in comparison with open pit mining, in underground, by using underground mining we remove considerably less amount of uranium ore. So this is the picture. In here in situ leaching process has been shown. So see what is the technique here. See, this is the mining solution from the processing plant. Okay, so from processing plant this hole has been created. So from processing plant mining solution will be sent in the deep earth layer. Okay, so this is the way for sending the mining solution. Okay, so from processing plant mining solution will be sent through this pipeline to the earth layer, okay, where uranium deposits are there. Okay, so these are the uranium deposits that has been shown here. Okay, so then here pumping system is there, so it will send the uranium deposits, okay, through this pipeline to the processing unit. Okay, so here we will receive the uranium solution. Okay, so this is the in situ leaching process. Okay, so through one hole uranium mining solution will be sent to the earth layer, so that uranium ore can be received through this pipeline. Okay, so two holes are here. Okay, in situ leaching process, through one hole mining solution is being sent through the earth layer, and another one is there for receiving the uranium solution from the earth layer. Okay, in the processing plant itself we will receive the uranium solution. So the milling process creates a waste by byproducts known as uranium trailing. Okay, so here this is the milling process. Okay, so in milling process uranium trailings will be created, that is the waste product, which is the residual. Okay, so here residual material are there. Okay, so these tailing contains radium, which decays to radioactive gas, radon and other toxic material which are heavy metals. Okay, so when we send the mining solution to the earth layer, so uranium or uranium solution will be received at the processing plant, but this also creates the uranium tailings, and tailings are the wastage. Okay, so these are the radioactive elements. So tailing pose a potential safety and public hazards, and for that reason they are isolated in engineered facility near the mine. Okay, so these tailing products can be hazardous and it can be unsafe for the public health. So for this reason these tailings need to be deposited from the mining. Okay, so there are some other facilities, some created facilities, some created facility is there. Okay, so where tailings will be deposited. So the uranium oxide product of uranium mill is not directly usable as we had seen U3O8. Okay, so U3O8 is not directly usable, okay, as a fuel. So we need to the processing. We need processing for that. So uranium oxide product of uranium mill is not directly usable as the fuel for a nuclear reactor, and additional processing is required. So U3O8, so the form or isotope of uranium which is fissile is U235 isotope. Okay, the remainder is a U238. So feasible is U235. So the most kinds of reactor, maximum of the reactor, for maximum of the reactor, the concentration of fissile U235 isotope needs to be increased. Okay, so as we had seen in U3O8, the 0.7% of U235 is available. Okay, so we need to increase this fissile uranium. So nuclear reactor, most of the nuclear reactor need percentage of U235 as 3 to 5%. So we need to enrich this. Okay, so this is done by the process of enrichment. Okay, so which requires the uranium to be in a gaseous form. Uranium oxide concentrate is therefore first converted to uranium hexafluoride. Okay, U3O8 will be converted into UF6. Okay, which is a gas at relatively low temperature. Okay, so this is done by the enrichment process. So at a conversion facility, the uranium oxide is first refined to uranium dioxide, which can be used as a fuel for those type of reactors that do not require enriched uranium. Some of the nuclear reactors are there which don't require enriched uranium. Okay, so in that we use uranium oxide can be first refined into uranium dioxide. So some of the nuclear reactors uses uranium dioxide also. So most is then converted into uranium hexafluoride UF6. Okay, which is ready in the enrichment plant. The main hazard of this stage of the fuel cycle is the use of hydrogen fluoride. Okay, so from uranium oxide, uranium fluoride is extracted with the help of hydrogen fluoride. So this is the hazardous stage. So the uranium hexafluoride is then drained into cylinders where it solidifies. Okay, so these strong metal containers are shipped to the enrichment plant. So Next is the enrichment process. The enrichment process separates gaseous uranium hexafluoride into two streams, one being enriched to the required level and known as the low enriched uranium, and the other stream is progressively depleted into U-35, that is called as the tails and simply depleted uranium. So there are two enrichment process in large commercial scale, each of which uses hexafluoride. Okay, each of which uses uranium hexafluoride gas as feed. Diffusion and centrifuge. There are two types of enrichment process. One is diffusion, one is centrifuge. So these processes, in both these processes, use of physical properties of molecules are there. Okay, so these processes both use the physical properties of molecules, specifically the 1% mass difference between the two uranium isotopes to separate them. Okay, so the product of this stage of nuclear fuel cycle is enriched uranium hexafluoride, okay, so which is reconverted to produce enriched uranium oxide. Okay, up to this point the fuel material can be considered fungible. Okay, though because enrichment levels may vary, but fuel fabrication involves very specific design. Okay, so reactor fuel is generally in the form of ceramic pellets. Okay, so these are formed from the from pressed uranium oxide, okay, which is sintered, okay, sintered at high temperature, that is a temperature should be 1400 degrees Celsius. Okay, so uranium oxide reactor fuel, basically it is a ceramic pellet, and it is basically formed by pressing the uranium oxide at the high temperature. Okay, this process is called as the sintering. So the pellets are then encased in metal tubes to form fuel rods. Okay, so which are arranged into a fuel assembly ready for introduction into the reactor. So this is the process by which we create the uranium rods for the nuclear reactor. So the dimension of fuel pellets and other components of the fuel assembly are precisely controlled to ensure consistency in the characteristics of the fuel. So the size and the components, those are involved. That means metallic portions are there over which this fuel rods will be sintered. Okay, so inside the metallic tubes, so size of the fuel pellets and other these metallic tubes, these are controlled, precisely controlled to ensure the consistency of the fuel characteristics. Okay, so inside a nuclear reactor, the nuclei of U-235 atom splits. Okay, as we know, so there is fission process in the nuclear reactor. So inside nuclear reactor, nuclei of U-235 will be fissioned, and in this process energy will be released. Okay, so this energy is used to heat water, and then the enormous energy is released when fission process is there. Okay, so this enormous released energy after fission will be used for heating up the water, and this will form the steam. So this steam will be used to rotate the turbine. Okay, so the steam is used to drive a turbine connected to a generator which produces electricity. Okay, so some of the U-238 in the fuel is turned into plutonium. Okay, that we had seen in the fuel cycle diagram, that some of the uranium during the enrichment process, some of the uranium 235 are converted into the U-238 fuel. Okay, so some of this will be converted into the plutonium, okay, in the nuclear reactor. So some of the U-235 in the fuel will be turned into the plutonium in the nuclear reactor. So the main plutonium isotope is also fissile, and this yields about 1/3 of the energy in a typical nuclear reactor. Okay, so plutonium are also fissile. So once fission process will be there through the plutonium nuclei also, so it will yield the 1/3 of the energy, that 1/3 of the total energy within the nuclear reactor. So the fissioning of uranium and the plutonium generated in the process is used as a source of heat in the nuclear power station, in the same way that we use by burning the coal, gas and oil. okay, as a source of heat in a fossil fuel plant. Okay, so mainly what we do in the nuclear reactor, that by the fissioning of the uranium and plutonium, which are the byproduct in the nuclear reactor, so we generate the heat. Okay, in the fuel, in the fission process, there are numerous energy is being released. Okay, so by fissioning of uranium and the byproduct plutonium, there are numerous energy is being released in the nuclear reactor, and this energy is used for burning the for generating the steam, you can say, in the nuclear plant. Okay, so the same, in the same way we use coal, gas or oil in the conventional power plant. Okay, so with time, the concentration of fission fragments and heavy metals formed in the same way as the plutonium in the field will increase to point where it is no longer practical to continue the use of the fuel. Okay, so it is generally after 12 to 24 months, the spent fuel cycle is being removed from the reactor. Okay, so there is no benefit for using the same nuclear fuel for so long time. So when removed from the reactor, the fuel will be emitting both radiation, principally from the fission fragment and the heat. Okay, so used fuel emit the radiation. Okay, so and heat also. So used fuel is unloaded into a storage pond immediately adjacent to the reactor to allow the radiation level to decrease. Okay, so these are being dumped into a storage adjacent to the nuclear reactor. Okay, used fuel will be dumped into the pondage. So in the pond, the water shields the radiation and absorbs the heat. So used fuel is held in such a pool for several months to several years, depending on which material is releasing the emission. Okay, so it may be transferred to ventilated dry storage on site. So used fuel is about 94% U-238, but it also contains 1% of U-235 that has not fissioned, and almost 1% plutonium, 4% fission products, which are highly radioactive, with other transuranic elements formed in the reactor. So in our reprocessing facility, the used fuel is separated into three components: uranium, plutonium and waste, which contains fission products. So reprocessing enables recycling of uranium and plutonium into the fresh fuel and produces the significantly reduced amount of waste. Okay, so that in the reprocessing facility, dumped or used fuel, nuclear fuel, will be separated into three components: uranium, plutonium and the waste. Okay, so uranium and plutonium will be further reprocessed for producing a new fuel. So and the wastage are then dumped. So wastage from the nuclear fuel cycle are categorized as high, medium and low level wastage by the amount of radiation that they emit. Okay, so these wastage come from the number of sources and include low level waste produced at all the stages of fuel cycle, intermediate level waste produced during reactor operation and by reprocessing, and high level waste, which is a waste containing fission products by reprocessing, and in many countries the used fuel itself, that is the high level waste. The fission products and their radiation effects are too dangerous and it can be considered as poisonous, okay, carcinogenic, okay, mutagens and tetrogens. So nobody wants any more. There are, as we know, Chernobyl incident was there, Hiroshima and Nagasaki nuclear weapon explosions were there. So and for those incidences, consequences are still visible. Okay, so after so many long year also, so we can easily find the disadvantages, or you can easily find the loophole or the drawback of this incidence. So the fission products have half lives from a fraction of second to millions of years. So engineers are also worried about storage of these radioactive wastage until they reach to a safe level of decay. Okay, So at nuclear plant, so these wastage are also a part which need to be taken care of. So nuclear industries strongly believe in safety first and foremost slogan. Okay, so for all the nuclear plant, so for all the nuclear plant, so it is main slogan for their working is that safety first and foremost, because nobody want any other nuclear incidences. Those are already for which we are already seeing the consequences. So first point is protect public health and safety. Okay, in this point, so first priority is for ensuring the public health and safety. So first point, we need to reduce the risk of from the releases of radioactivity to acceptable level. Okay, so first point is that we need to take care of the nuclear waste until decay from that reaches to a safe level. Okay, so it will reduce the risk from the radioactivity. Okay, so second point is that protect plant worker health and safety. Okay, so first priority is for public health, second priority is for health of staff and worker, those are there in the nuclear plant itself. So we need to provide a safe and working environment and reduce risk of injury. Okay, so third point is to protect the environment. So we need to provide design that complies with all federal, state and local requirement. Okay, so from country to country, and there are different set of rules for protection of environment. So we need to design the nuclear reactor in such a location and in such a way that all the environmental aspects should not be harmed. Okay, so the next is to protect the plant investment. So we need to provide the plant design, equipment and operating maintenance practices to preserve investor equity and return award. Okay, so also the plant design and equipment and other maintenance should be in such a way that the investor, which may be government entity or which may be private entity, so that should get an award and equity in terms of return. So fundamental nuclear safeties are there. So to protect individuals, the members of the general public and natural environmental from harm resulting from the commissioning, operation and decommissioning of nuclear facility by establishing and maintaining all the nuclear facility in effective way. Okay, so we need to first is to maintain the general public health and natural environment from the radiological hazards. Okay, so there should be effective defense against the radioactive hazards, and the defense should be in such a way that it should protect general public health, natural environment also. So second one is radiation protection, to ensure that during all operation states of the nuclear facility, the radiation exposure of the persons working within the facility as well as living in the vicinity of the nuclear plant, okay, so that should not get affected by any planned or unplanned release of radioactive material. Okay, so in either waterborne or airborne effluents. Okay, so see, a rule has been passed that is called as the ALARA. Okay, so as low as reasonably achievable. Okay, so since nuclear plants are there, so and the population that those are living in the vicinity of the nuclear plant, that should not get affected in any way by the nuclear radiation. Okay, so and not only the airborne radiation, they should not get affected by the waterborne radiation also. Okay, since these materials are dumped into the pondage, okay, where they used to continue the emission through from several months to several years. Okay, so there are chances that these radiation may contaminate the water of that particular area. Okay, so that should not be there. this should be maintained, that people or the population residing in the vicinity of the nuclear plant as well as in the plant itself, they should not be affected with any kind of waterborne or airborne radiation. Okay, so technical safety should be there to take all reasonably practicable measures and to mitigate their consequences should they occur. Okay, so these are the few points that should be maintained. Okay, so these are the some points that should be always remember while designing the nuclear plant. So these are the that high quality design should be there, and construction should be in a well mannered. So this is okay. So for next and the last ultimate our summary is that prevention, monitoring and action. So see, there will be some unplanned and planned radiation. Okay, but we need to be prepared for that. Okay, so first is we need to design in a preventive way, but there should be continuous monitoring, and if any unplanned or any such kind of incidences is occurring, then there should be immediate action. So this is all about the today's discussion. Thank you all.